So welcome all of you, a warm welcome to all of you to today's user preparation webinar on EPS-SG radio occultation mission. I am Srireka Doniparambil. I am the EPS-SG user preparation manager at EUMETSAT, and together with my colleague Stefan Bijinski, who is the MTG user preparation manager, we have been organizing this series of next generation user preparation webinar on all observation missions on board MTG and EPS-SG, which are EUMETSAT's next generation polar and geostationary satellite programs. And today we are on the 7th in this series on the radio occultation mission. So those of you some of you might have, we have been organizing this over the last 1 year. So we started with IRS and ERC&G last October, and then we had one on lightning imager, we had on scatterometer, we had on FCI and MET-image, 3MI, and 2 weeks ago we had one on the microwave missions. So some of you might have attended those, at least a couple of them, and but we look forward to new participants. So this is why I try to put this into context, the introduction. So we are organizing this session on radio occultation in 2 days. So today you will hear from Christian Marquardt more on the first talk on the radio occultation techniques, the basics, and then we will move to Ricardo Notapetro, who will talk on the more on the radio occultation mission in onboard EPS-SG. He will talk more on the products and their formats and dissemination. And then we have Ian Culverwell. He's from Met Office and part of the ROMSAF, the Radio Occultation Metrology Satellite Application Facility. He will talk on the radio occultation processing package. And that's what we will have today. And tomorrow we will go to more exciting, should I say, this is on the applications of radio occultation in NWP, in climate, and the space weather. So before I move to Christian, let me just say some logistics. We've, like I said, those who have attended before might already know, we use the Slido tool for our interaction purposes. So basically, if you have any questions, you will go to slido.com and you will be prompted to enter a code. So use the NG-RO. You will see in the chat message this code if you have a look there, and then you are in the tool, and it's a web-based tool, and you can enter your questions anonymously, or if you want to put your name, do that. And you can post your questions there, and during the time in the agenda for questions, we will take up all the questions that you have asked, the maximum that we can, and all those questions that we cannot handle during that time, we will take it offline and try to answer to you after the webinar. And the other thing is that we will provide not just you see that the session is recorded. So we will provide the recording, the slide set, and also the questions with answers to you after the webinar. So with that, I will hand over to Christian Marquardt. And Christian.
Thank you very much. My name is Christian Marquardt, and I'm leading the radio occultation team within EUMETSAT, and we are dealing with all the scientific things around radio occultation measurements. And you will hear some of my colleagues from within EUMETSAT and also from the ROMSAF today and tomorrow, talking about radio occultations. So I try to share my screen, and I hope that is working fine, like this one. Okay, at least it tells me so that it is. I wanted to start the day with introducing some basics about radio occultation. I do apologize if it's becoming too simplistic. Let me know in the chat, and I will also apologize if it's becoming too complicated or too detailed. I try to find a balance, and I'm not sure if I got that right, but we will see. What I want to talk about is a little bit about global navigation satellite system, really the very basic ideas on how it works. And then come finally to radio occultation measurements that we are talking about today. I will briefly go to which steps we do in this processing towards the main products. And finally, I will have 1 or 2 slides thinking about what is contributing to the uncertainty of radio occultation measurements, so that you have a little bit of background for the next talks coming. So let's start with GNSS, or Global Navigation Satellite Systems. Probably the most famous and well-known one is GPS, the Global Positioning System. That is primarily a constellation run by the United States Air Force, I think. And nominally, it consists of 24 satellites orbiting the Earth in 6 different orbit planes at an altitude of about 20,000 kilometers above the Earth's surface. And one satellite circles the Earth in about 12 hours. So an orbit takes half a day. And the purpose of that constellation is to allow navigation with a very high precision. That is, finding out where you are on the surface of the Earth. And the constellation has been designed so that with 24 satellites, you will, wherever you are on the world, you will see at least 4 satellites. And actually right now we are running, I think, 31 satellites, which are really operational. And with that, you typically see something 7 or 6 or 8 satellites at any time. So how can a constellation like that help you with finding out where you are? And that is essentially finding out by knowing what the distance to that satellite is and where the satellite itself is right now. Because if you do know that, then you know that you are somewhere on this sphere with a satellite in the center. And because you know the range, you know the radius of the sphere. If you know the same for 2 satellites, then you already know where you are on the intersection between the 2 corresponding spheres. So that will be a circle. And if you do the same for the 3rd satellite, then essentially that boils down in most cases to just 2 points where you can reasonably be. And if you know that you are on the Earth's surface, then that usually is actually enough to find out where you are there. And then, of course, if you're taking the information from more satellites, then you can have richer estimate, it becomes more precise. So what you need then is you want to know where all these GPS satellites are, and you want to know how far you are away from them. And how can satellites tell you that? Because in the end, they are just sending you a signal in a certain frequency. And the answer to that is in the structure of the signals. So what GPS satellites do is they, apart from the plain carrier frequency, where they send their signals, which happens to be the same frequency, at least for the more modern ones, GPS, and so on, they are modulating what's called a code on top of this carrier frequency, which consists of zeros and ones. So here's a 0, a 1 at 1 at 0, 0, 0, 1, 0, 1, 0. And that so-called pseudo-random code, that is unique for every satellite. And you receiving this signals, you can identify the satellite based on the sequence of zeros and ones being modulated on top of the signal. And even better that, if you find the same portion of that code that you are receiving, if you know when the satellite has sent it off to you, then you can calculate how long the satellite took, how long the signal took to reach you. And multiplying that by the speed of light is giving you the distance. So that's fundamentally how GPS or any global navigation satellite system works. You are measuring the time difference between the transmission and the reception of the signal. The second part we said we need to know is where that other satellite really is. And what comes into that is then that apart from these pseudo-random codes that identify each satellite uniquely, they have a secondary modulation on the same carrier frequency. And that is encoding, well, indeed, the position of itself and also of all the other GPS satellites in this case. And it's also in regular intervals telling you when it sent off that particular bit of this whole code business. So by taking that information together, the receiver can sort out which satellite sent it off, where the satellite was at the time of sending it, and what the time was. And then it has a clock of itself. It's calculating the time difference. You have the range or the distance to the other satellite. Now, of course, 2 clocks never run perfectly synchronously. And if you are thinking about you are tracking signals from 7 or 8 satellites, and all of them are a little bit slightly off. Your own clock is also slightly off. And you're doing that as part of the estimation process from where you are. You are also trying to find out what is the difference in the clock estimates. So you need a force measurement or a force satellite where to take measurements from in order to resolve these 4 unknowns, that is 3 spatial coordinates and 1 clock or time offset coordinate. So that is, in order for that to work, you need at least 4 satellites where you can track signals from. And that is why the GPS and other GNSS systems are designed so that you can always see at least 4 of these satellites at any time. Now, getting a little bit more into the details about what GNSS receivers do. What I've described to you is what's called the pseudo range, because you get it by tracking these codes, which are modulated onto the carrier frequencies on which these satellites are sending the signals. And if you take the GPS satellite positions as they are contained in this secondary navigation bit or navigation message code, then you are getting a positioning accuracy of probably a few meters. That is what our smartphones do, or handheld GPS receivers. If you want to become more precise than that, then you can go one step farther. And once you are tracking, that's called tracking, right? If you know where you are on the code. Once you are tracking the code, what you can do is you can go to the actual carrier frequency and how that is oscillating around as an electromagnetic field. That then is called carrier phase tracking, and that is even more precise. That doesn't give you an absolute range because there is no time information encoded on the carrier phase itself, because it's just a sine oscillation basically. But once you have track of the carrier phase and you don't lose it, you know very, very precisely how the range, the distance, has developed over time. And for example, when we are looking to the GRASS instrument, we know that the carrier phase noise on the GPS L1 frequency, that is about 1/3 of a millimeter. So it's a very, very precise measurements of the carrier phase. And if you then use precise GPS positions and these carrier phase measurements, and you do really well, then people have achieved to do something like positioning accuracies in the order of a few centimeters or even below a centimeter. Now GPS, I said that was the first and probably the best known GNSS system, but there are other ones, and I come to that in a moment. The most important ones are probably GLONASS, the Russian system, then of course Galileo, the European counterpart. China is flying a constellation called Beidou, or Compass in plain English, and then there are regional ones. For example, there's a Japanese QZSS system. These are the most important ones for radio occultations. But before we come to that one, I want to finally come to the radio occultations themselves. So here is a live view of one of the METOP, okay, it's not really a live view, right? One of the METOP satellites. And for the radio occultation, the satellite has 3 antennas that we are interested in. The one that is sticking out in the front, and on the other side there is another one. These are the occultation antenna, and then there is a small antenna on top of the roof of the satellite. While the satellite is flying around Earth, we have these, in case of GRASS, GPS satellites flying much higher than that. And the receiver on board of the GRASS instrument is tracking the signals from them through the zenith antenna or the roof antenna to find out where the satellite is. Now, every once in a while, one of the GPS satellites is setting behind the Earth's horizon. This is what's happening here. And if I may stop that for a moment, the yellow link, that is now taken from one of the occultation antennas. And in this case, it is one of the forward-looking ones. So we are looking forward and backward from the point of view of the spacecraft. And what happens now is that the signals which have been traveling through vacuum now are traveling horizontally through the atmosphere. And the atmosphere is a refractive medium, so it acts like a lens. And the lower down the ray is sinking into the atmosphere, the more dense the atmosphere becomes, and the larger the refractive index becomes. And what happens, as in plain optics, when the measurement proceeds, then we are bending this ray path towards Earth. And that is what you see a little bit in this animation that is starting here And now it turns out that that bending is somehow related to the temperature and the humidity and the pressure. And as a third one, sorry. Oops. I tend to find the wrong button. Here we go. It's related to temperature and moisture, and also the electron density in the ionosphere. So these three are the key parameters that define the refractive index of the atmosphere and ionosphere for radio signals in the frequency range for GNSS signals. And by the way, they are somewhere between 1 and maybe 1.5 gigahertz typically. Now, if we have in particular a vertical gradient in that refractive index, what it means is that we are bending the rays towards the surface. And here in this figure, you see essentially the same geometry. Here's our receiver in low orbit. Here's our transmitter, and the rays go from here. Then they are going horizontally through the atmosphere, and they are getting bent before they are reaching the receiver. And the quantity we are interested in is the angle, the amount, how strong that bending is. And basically, the lower you get down into the atmosphere, the stronger the bending gets. Now, physically, if there wouldn't be an atmosphere, if there wouldn't be Earth, the signals would just travel along the straight line. And the path along the red line is a little bit longer. So the atmosphere is creating what we call an excess path that the signals have to travel. Another way to say is they are getting a little bit delayed. Now, both satellites, obviously, they are moving. So because they are moving all the time, there is a Doppler shift in the signals. And when we take an occultation measurements and this excess path is growing and growing during the occultation, then that means there is also a change in the Doppler compared to the straight line Doppler. We call that the excess Doppler. And that, it turns out, that is the interesting quantity we are interested in. Because if you know the excess Doppler, and if you know the positions and the velocities of the two satellites being involved in this occultation measurements, then we can calculate from mostly geometrical considerations how large that bending angle is. And that is precisely what we are doing. So we are taking the measurements of the carrier phases, we are calculating the excess Doppler in the end, we are taking the position and the velocity of all the satellites, and we are calculating the bending angle essentially as a function of height. Now, obviously, we need to know where the satellites are. And it turns out that in order to have a reasonably good measurement or a very good measurement, you need something in the order of maybe a couple of 10 centimeters for the satellite positions. I mentioned that the real quantity we are interested in is the Doppler, which comes from the relative motion of the satellites. So the really driving requirement is the uncertainty we have in the satellite's velocity. And a typical requirement for that is that the velocity needs to be known in the order of 0.1 millimeter per second, which is enormously good if you think about it. I mean, I don't know how fast my car is with that accuracy, but for the satellites, we do that. And the formal requirement, as we will hear later from Ricardo for EPS-SG, for example, is even better. That is something like 0.05 millimeters per second. Now, in that whole process of estimating the bending angles from these measurements, what we do assume is that the atmosphere is spherically symmetric around the tangent point. That is, we do not have any horizontal gradients. And if you're looking in the ionosphere, the assumption there is, of course, the same. As I mentioned, the ionosphere, electromagnetic signals traveling through the ionosphere at different frequencies are slightly differently affected by the refraction. So the amount of bending is different for different frequencies. That is why we always use two frequencies in radio occultation. And we can do two things with it. We can take the two frequencies and combine the measurements in a way that we are removing the ionospheric effect. And what we get then is a profile of the bending angle in the neutral atmosphere, or the profile that is being caused by the neutral atmosphere alone without the ionospheric influence. And the other way of using this data is when we are high up enough so that the neutral atmosphere doesn't matter, we can also use the data from the two frequency measurements, combine them in a slightly different way, and then we get an information about the most important ionospheric parameters. That is the delay of the signals caused by the ionosphere. And we can turn that, for example, into information about electron density. Now, I won't go into too much detail, but I would like to show you one example of how the measurements look like and how the bending angles look like that we get out of that. And the example is here. So in the top row, this is the function of time during setting occultations, which is very old, from 2012. And it's a setting occultation, so we are starting high up in the atmosphere, and there's not much impact on the excess phases, but the lower we get, then suddenly the excess phase is increasing. And you see it's a couple of 100 meters for this orbit altitude where we are. And these are the different frequencies. We call them L1 and L2 in case of GPS, and for GRASS, because that is what we are measuring. And when we turn that into a bending angle, then we have a bending angle for the first frequency, L1, that is about 1.5 gigahertz. And for L2, that is about 1.2 gigahertz, 1.2 and a bit. And you see they differ high up, and when we are getting down into lower altitudes, and they don't. By the way, the altitude scale, that is from the surface up to about 80 kilometers, which is the measurement range of GRASS. We don't measure higher with that one. Well, if we combine these two bending angles, we are getting to something like a neutral atmospheric bending angle. And because the atmosphere is getting thinner and thinner, this is just getting smaller and smaller. And at some point, we are getting into a noise region higher. If you zoom into the troposphere, then around 17 kilometers, that is a tropical occultation. So around here, that is an indication of the tropopause. And remember that refractive index in the stratosphere mostly depends on the temperature. And when we are getting down into the troposphere lower down, then we become sensitive to the moisture as well. And here on the right is a zoom in of the bending angle that we get with our current retrieval in the lowest few kilometers. And what we are showing here is the impact altitude. So that is multiplied with the refractive index. So the surface in this altitude scale is around 1.7. So we have an occultation here, which isn't going completely to the ground, but very close. You see lots of interesting structure there, and that is all caused by water vapor. We'll come back to that. We'll come back to that particular occultations in a moment, very likely. But I would like to summarize a little bit these characteristics that we so far have seen. So first of all, we have limb measurements. That is, we are looking horizontally through the atmosphere, and we have no telescopes or anything involved. It is the vertical resolution is determined by the physics of refraction, so by geometrical optics. How large, how thick is the geometrical optics ray? And it turns out that that is somewhere from a few hundred meters to maybe 1.5 kilometers. So we have a very vertical resolution. On the other hand, because we are going horizontally through the atmosphere, the information comes from a region which is probably in the order of 250 to 300 or maybe 400 kilometers. And because the satellites are moving, the tangential point, while sinking down or rising up in case of rising occultations, is also moving by about the same amount. So we are looking into a vertically very high resolved measurement, but which horizontally has a much lower resolution than you are used to from nadir sounding occultations, for example. Of course, most information comes from the area around the tangent point, but it's definitely not a point measurement. On the other hand, we have a very high vertical resolutions. So I mentioned that the GNSS frequency are in the range between 1 and 1.5 gigahertz. And of course, they have been chosen to be there because they are not very much affected by clouds, in particular by cloud water droplets. So in that sense, radio occultations are weather independent. We are doing a frequency measurement, and the frequency or time measurement from the GPS system is linked to the world's network of atomic clocks, which is defining how we measure time. So we have, through the measurement, a traceability to SI standards, and the accuracy in time measurements, of course, is very good. And these are all benefits of GNSS RO. And because it's really just a radio receiver and it's not doing anything complicated, there's no optics that can age or mirrors that can degrade over time. There are no known instrument or calibration drifts. And that means there is no absolute bias correction required. Radio occultation is one of the few measurement systems which doesn't require bias corrections in their application. I mentioned different GNSS systems and the GPS. That is what we use in GRASS. By now, there are more. Galileo, Europe's counterpart that has currently 24 operational satellites. Then there is GLONASS, which we are not going to use in EPS-SG. There is Beidou, that is China's counterpart. They have 30 satellites in this medium Earth orbit, and a couple of few more somewhat higher, which we are not using. There is, for example, the QZSS system, but that only consists of 4 satellites, and that's why in EPS-SG we will not be exploiting this one either. When you're looking at the frequency band, so I simplified a lot. There are essentially 3 different frequency bands. L1, which is at 1.5 gigahertz, L2, which is 1.2 and a bit, and L5, which is 1.1 and a bit gigahertz, on which these satellites are measuring. And you see that the legacy systems, the older systems, they usually are working on L1 and L2, and Galileo and also Beidou, they are also introducing this L5 frequency. Modernized GPS will have that one as well. And yeah, these are the systems we have. If you want to have a rule of thumb on how many occultations you get, it's a normal constellation of 24 satellites, and you have both rising and setting occultations. You are getting about 500 occultations a day if your receiver is operating 24 hours. Obviously, the global distribution depends on the orbit geometry. If you have sun-synchronous orbits, you are distributing the occultations relatively evenly, but there is a lower density in the tropics, just because the area is so much larger. And if you are thinking about the local time distribution, if we are on a fixed local time with the orbit, then individual occultations will be 3,000 or 3,500 kilometers away from the ground track, but they will still, of course, be close to that local time. You will not get a global coverage in local time from a single satellite on the sun synchronous orbit. So from that, actually, you can, what we are doing when we are doing radio occultation retrieval, and we first need precise orbits of all these GNSS satellites, and that is provided to us through a service called the Radio Occultation Support Network. That is a company in Spain currently doing that, and they are operationally providing us with high precision orbits of these satellites. And then at EUMETSAT, we start with carrying out the precise orbit determination for the satellite using the zenith antenna data, and then we are calculating the excess phases. That is the difference between the straight line connection. And we call that the level 1A. And from there, we calculate bending angle profiles for each frequency. We combine them, that is this ionospheric correction. And then, of course, we do smoothing and thinning and georeferencing and quality control and God knows what. And that we call level 1B, or bending angle profiles. And then the ROM stuff, radio occultation meteorology stuff, comes into place, because they take our level 1B products and then they do higher level products, in particular this refractivity or refractive index, and temperature and moisture profiles that we call level 2. And then they don't have climate projects, but climate products, you know, zonal means, height of these so many hectopascal, that's I think called level 3. And they also provide software that you can use to process the data yourself, like the radio occultation processing package that Ian will talk about later today. I would like, before I come to an end, I would like to come to the error characteristics of radio occultation soundings and how we think they look like. And to start with, this is another schematic view on occultation, how it has happened over time. What you do see is Earth here, there is a satellite flying around, and we see individual rays coming from a GPS satellite, which is far away. And then here, this is the amplitude or the SNR of the 2 frequencies. Essentially, this one is the L1 in this case, and that's L2. So let's not care about the details. And what you think is, and that is what I said, is the deeper you are going, the stronger the bending is. So we are spreading out the signals over longer and longer parts of the arc. So we are spreading out the energy. So SNR is dropping while we are coming down, and that's fine. And if you stick in that picture, then it would remain very simple, because rays would just be bent more and more. No, that is actually not what's happening. Because what we assume here is that at any moment in time when we are measuring this one, we only get one ray coming to the receiver, one single tone. As long as that goes, it's very easy to retrieve them. And this is about the regime that we have in this part of the measurements. What happens when the atmosphere is becoming more complicated, say on top of a cloud, you have a very strong gradient in humidity, and that is in reflectivity, and then this rate will be bent quite a lot. But if you are looking through the atmosphere a little bit lower, then there is no strong vertical gradient anymore, and it will not be bent that much. So we have rays crossing, multiple tones, radio signals interfering constructively and destructively, large fluctuations of amplitude. And in order for that to get, we need two things. We need retrieval algorithms that can disentangle this overlapping of waves, this interference things, and we call them wave optics algorithms. And the other thing is the receiver has to be able to still follow the signals to track them. And that is not the standard thing that your handheld GPS receiver would do, but we are using technologies called like open loop, and you will hear that a lot. So for tropospheric measurements, an important part is you need receivers that can do open loop tracking, and you need wave optics algorithm to process the data properly. And still, it is difficult in the tropics. And the reason for that is, if you remember, I said in the beginning, we have this assumption that we have horizontal homogeneity, no horizontal gradients. If we are in the stratosphere, where the horizontal scales are probably several thousand kilometers maybe, or at least many, many hundreds, then over these 200, 300, 400 kilometers, there is not much horizontal variations in the atmosphere. So there it works fine. If you're going into the lowest few kilometers of the troposphere with lots of convection, rain, precipitation, different kinds of clouds, different heights of clouds, that is not horizontally homogeneous anymore. So the assumptions that we do in the retrieval to some degree break down, and that is increasing the error budget of the radio occultations. I'm skipping two slides because I'm getting out of, I'm running out of time. But I want to come back with a final figure where we think what parts of a receiver or of a radio occultation system is contributing to the uncertainty of the level 1B products in particular. But of course, that translates to higher level products like temperature profiles as well. And if you're starting high up, then one, you remember we have to remove the ionospheric effect. So if you don't do that well, or if the ionosphere is very active, then you might have ionospheric residual errors that are contributing to the error budget. And the other thing is the instrument thermal noise, so the quality of the clocks and the size of the antennas, for example. So above 35 kilometers or 30 to 35 kilometers, you see differences in the instrumentation to a large degree. On the figure on the right, this is the bias as function of altitude against ECMWF short-range forecast, and this is the standard deviations for two measurement systems. I do not even want to mention, I don't even want to go into details which is what. There's one that has very large antennas, high SNRs, and that gives you a nice compact around the average measurement. And there is another one which is a very small satellite, much lower SNRs, and you see the increased level of noise at altitudes above maybe 35 kilometers. Interestingly, if you average enough, it has no detrimental impact on the biases. If you apply the same processing, that I should say, this is two different RO missions with the same processing applied, no fine-tuning of anything. The really nice spot for radio occultation is that green altitude range. That is from the upper troposphere, say 8 kilometers up to 30 or 35 kilometers. Because here, the main impact on the measurement uncertainty is coming from horizontal gradients. And as we said, in the stratosphere, they are not very large. But instrument noise becomes less and less of an issue. And what we see here is that in this altitude range, even the lower SNR measurement looks quite good. And you could smooth it a little bit more, and then they would be on top or even better than this red line. And that is the beauty of radio occultations. You can go a long way with cheaper instrumentation if you want that, and if you can, for example, get more profiles out of that. So that's a very good thing. You still, of course, want to have the high quality measurement as a reference, and I think that is where we are heading with GRASS and also with SG in my view. If you're going to the lower troposphere, so that is below 8 kilometers, that is a yellow range. So here is where the humidity becomes, very variable, where the spherical homogeneity condition isn't really valid anymore. And that is where, of course, the wave optics processing becomes important. but also the tracking algorithms that are implemented in the instruments. And I believe, but that is an open point for discussion, is that the SNR plays a role here because we are cutting off data depending on the SNR and all of that. So that's an interesting topic for the science. But what I want you to keep in mind is that we have a very nice range in the middle where all RO missions really perform well. When you're going above 30 or 35 kilometers, the high SNR missions do perform better. You see differences in the instrument from the instrument characteristics, and the troposphere region is really a difficult one still. And that is why the uncertainties are going up here quite. Now, that was my talk. Thank you very much for listening. I hope you have many questions.
Thanks, Christian. Very good introduction for the day, actually, for tomorrow's presentations too. I think that you went through this processing chain, you know, the retrieval. That's a good introduction to all the talks that are coming up today and tomorrow. But let's have a look at the questions, Christian.
Mm-hmm.
What I will do is I will bring up I will stop sharing your screen.
Yes.
Yeah. And then I will bring up my question screen. In the meantime, please, you can, the participants, you can actually go back and go to Slido and try to post your questions till Christian is here. I don't know what you see now, but is that showing something? Yes.
I can see it.
So Christian.
Yes, does GRASS and the ones before has dual frequency for ionospheric measurements? So the answer is GRASS doesn't. When GRASS was designed, the idea was that nobody cares about the ionosphere. However, all other radio occultation missions do. We have recently extended the measurement range for METOP-A, so we are measuring up to 300 kilometers, and we will do so for METOP-B and C within this year, I hope, or maybe in January. So we will do some ionospheric processing for GRASS as well. EPS-SG is much better. They will be going up to 500. Ricardo is going to talk about that. Other missions go up to orbit height, so that can be up to 800 kilometers and produce that electron density profiles. Yes, RO receivers will be on both METOP-SGs. Is there a certificate of attendance issued for this webinar? I'm sorry, I can't answer that.
No, there is no certificate of attendance for this. Yeah.
Yeah. Does the antenna phase center variation play a role in the error budget, and can it be corrected? For GRASS, we have actually done calibration measurements for all the antennas on ground before the satellite launches, and for the Zenith antenna, we have done in-flight calibrations, and we are using them for the precise orbit, determination.
Sorry, did you lose it?
No,
yeah?
no.
Oh, okay.
I just try to answer. So we use them for GRASS. We use them. However, the other thing to say is that even for GRASS with big antennas, the phase variations are in the order of a few centimeters. So yeah, in principle, they play a role. We correct for them in EPS-SG. They are so small that we do not correct for them. And I think that is true for the most other RO missions. So yeah, you can take it into account. It's probably more important for the precise orbit determination because they're really every centimeter counts. In the radio occultation processing, because we are looking at the Doppler, so it's a derivative of the phase, as long as it doesn't change too quickly during the course of an occultation, the impact of carrier phase delays is essentially negligible. And the variation over the antenna over these 2 or 3 minutes is usually very small. So we probably don't need it.
So Christian, did you, this question, did the receiver know and save the information
Yes.
of which GNSS satellite it is tracking?
Yes, every single occultation comes with an information which RO satellite sent the signals, and at what time it was, what the frequencies were, and so on. Okay. And actually where the satellites were at the time, yes.
Okay. I think the other one, with reference to the slide number 14, why the Indian Regional Navigation System, IRNS, or NAVIC not included? Is it not supporting or useful for the RO work?
Very interesting. The secondary frequency that is used by INRS is really far away from the usual GNSS frequencies. And to my knowledge, no one has ever tried to build a receiver that can simultaneously track the standard L1, L2, L5 frequency bands on one hand. And then I think it's either X or S band. I have forgotten what the second frequency is. So I'm not aware of anyone trying to exploit. I mean, the first ones that have actually exploited the QZSS and Beidou and Galileo signals in practice was a commercial company called Spire. I know that Dallas Masters is in the audience, but they have really pioneered to demonstrate that all these GNSS systems work. But IRNS, because of that one very different frequency, I'm not aware of that anyone has ever tried so far.
Okay, Christian, I think this we answered, right? The phase center variation. So can we extract ionospheric information from phase file considering an altitude greater than 35?
No, I don't think so, because the ATM phase file, I mean, the ATM is for the neutral atmosphere. This is a UCA data format, and it's usually limited to data up to 120 kilometers. And there, the neutral atmospheric part is the most important one. That said, you do see that the bending angles at the two different frequencies that you can derive from that one, they are different. Also, you know, above 40 kilometers or so. So yeah, there is an ionospheric influence that you can try to get. But I mean, the ionosphere starts high up, right? Say above 80 kilometers or so. Sporadic E is around 120, and then the F layer comes in 300 or so.
Okay.
Atmospheric moisture profile data. I mean, one of the important things to remember is we are sensitive to the refractive index variations. And the refractive index variations is a combination of the temperature variation and the moisture and the specific humidity in the air. And because you only have one measurement, you have to provide one. So you usually take, for moisture retrievals, you take a background profile that is essentially nailing the temperature, and then you are calculating what is the moisture compared to that. At the same time, if you are going into the troposphere, the error bars of the measurements themselves get larger. So the error bars of the moisture profiles are getting larger. But there are a large number of projects and papers being written on the quality of water vapor profiles coming from radio occultation sounding. It is definitely good for research. If it is a high quality measurement of the humidity profile, that is, you know, as of high quality as the temperature measurements in the lower stratosphere, for example, that I would doubt. So the bending angles are, the moisture errors are just larger. But people have used it, yes.
One more question. We have time before we go for break. So the LEO has dual frequency receivers.
Yes, it has. Yes, all radio occultation receivers do it in dual frequency.
Good. That's all the questions, Christian. Thank you very much. And
Thank you very much.
Finished in time. Thank you. So we have 5 minutes break. So we meet at, we can meet at 12:50, a 6-minute break, let's say. We can meet at 2:50, which is the European, Central European summertime. And so in 6 minutes we meet. Thank you. Ricardo, you can start maybe bringing up your slide and get ready. We will start the talk in a minute, but you can bring up here.
Okay.
Yes, looks good.
Yeah, perfect.
No, not now. Now you have to go to the display settings and
Good now?
yeah, now it's good,
Yeah.
Ricardo. The
Perfect.
first slide, and You can start, actually. It's 14:50 now. Yeah.
Okay. Thank you very much, Srereka. So, hello to everyone. I am Riccardo Notarpietro, working at EUMETSAT, and I'm going to present you the radio occultation mission on board the EPS second generation, the products that we are going to deliver, and the data access. I'm doing this presentation on behalf of the radio occultation team at EUMETSAT. So I'm starting to provide you an overview of the radio occultation mission on board EPS second generation. I will give some comparisons, at least in terms of user requirements, between the radio occultation instrument on board the EPS-SG and his father, which is GRASS on board the EPS METOPS satellites that are currently flying. I'm going to provide you the detailed description of the radio occultation products we are going to deliver, their archiving and their dissemination. So, METOPS second generation. METOPS second generation is a constellation of 6 satellites flying in 3 pairs. Each pair has, of course, 2 satellites. The first one, the METOPS second generation A, is the satellite that is carrying on board all the sounding and optical imaging payloads. It is a huge satellite. Here is a quarter-sized model picture taken in our briefing gallery. It's really a big satellite. The lifetime is 7.5 years. It will fly on a sun-synchronous orbit at 835 kilometers with a revolution time of 101 minutes. The local time at the descending node when the subsat point is crossing the equator is 9:30 in the morning. So the payloads of these satellites are here listed. We have an infrared atmospheric sounder, the YASI-NG. We have the MWS, which is a microwave sounder. METIMAGE, which is a visible infrared imager. Then we have the radio occultation, and you can see here and here the 2 radio occultation antennas. Then we have a 3MI, which is a multi-viewing, multi-channel, multipolar imager. And finally, we have the Copernicus Sentinel-5 sounder, which is a sounder on the ultraviolet, visible, and infrared bandwidths. The second satellites of each pair, METOPS second generation B, hosts on board microwave imaging and sounding instruments. Again, is even bigger than the first one. The lifetime is the same, and it will share the same orbits as the METOPS second generation A. The payloads are the scatterometer. You can see here the big antennas of the scatterometer. The radio occultation, which is hosted also on board the METOPS second generation B. Here you can see the 2 radio occultation antennas. We have a microwave imager for precipitation instrument, which is MWI, ICI, which is an ice cloud imager, and then we have a data collection unit, which is called Argos 4. As a service, the EPS second generation will provide to the user a global service. So the 2 satellites, after having collecting data during their orbit, they are downloading the data to the polar stations. We have 2 polar stations, one at the Svalbard in the North Pole and the other at McMurdo in the South Pole. Data are repatriated to EUMETSAT, where they are processed and then delivered to the users. Radio occultation will have also a regional service. When the satellites are flying over this area of interest, the data are collected and sent down to the regional stations that are deployed here in this area, repatriated here are connected to the radio occultation antenna. correlators. This chip was developed under an European Space Agency contract some years ago. The AGA4 has 36 single frequency channels, and each channel is used to track the pilot or the data component in closed loop or in the open loop tracking mode on L1 or on L5 frequency. Just to provide you an overview of how the channels are allocated during one entire occultation, here is a picture. But before describing this, I would like to say that the occultation for EPS second generation will be tracked starting from 500 kilometer down to minus 300 kilometer SLTA, where SLTA is the straight line tangent altitude, which is basically the distance of the straight line connecting the two satellites from the Earth's surface. For setting occultation, so the signal starts to be tracked at 500 kilometer, only the pilot component in closed loop for both frequencies will be tracked. Then going down from 85 kilometers down to minus 250 kilometers, also the data component will be tracked. So in this case, we need two channels for each frequency to track, one for the pilot, the other for the data component. In parallel, starting from 30 kilometers down to minus 300 kilometers, the receiver will track both the pilot and the data component for both frequencies in open loop. This is aided by the closed loop tracking circuit, so we expect to have the signal more or less centered or somehow placed inside these 5 correlators, which are enough to track in open loop the signal. Overall, we need, so again here we need 4 channels, so we need 8 channels to follow the entire setting occultation. For what concerns the rising occultation, instead the things are a little bit more complex because we want to start tracking signals down from minus 300 kilometers. And we will start in tracking pilot and data component in open loop, but this time we don't have any help from the closed loop. So while the signal is rising from the local horizon, we need to have the signal centered somehow in the correlation banks. So the instrument has implemented on board a very accurate Doppler model, which is hiding the signal to be centered in these correlators. But 5 correlators were not enough. So we need 10 correlators to follow, at least in the first part, the tracking of the signal. Then from minus 38 kilometers to 30 kilometers, the signal is continuously tracking open loop, both the pilot and data component, but in this case, the signal will be expected to be in one channel and not in the other. So 5 correlators will be enough. Then in parallel, there will be the closed loop tracking for pilot and data up to 85 kilometers and only for the pilot component up to 500 kilometers. So we will have, again, the need of having the available 8 channels for following the entire rising occultations. So having the AGA4 receiver, 36 channels available, we can track contemporaneously 4 rising and 4 setting neutral atmospheric occultations and 2 rising and 2 settings ionospheric occultations. For the precise orbit determination, instead, the AGA4 receiver will track signals from 17 different GPS and Galileo satellites. The remaining channels are used to download, to store the ephemeris from the Beidou constellation. Anyway, at the end of the story, for each measurement epoch, we can combine open loop and closed loop pilot and data component together to have time series of phase and signal to noise ratios for each frequency, which are sampled at 200 Hz for the Galileo signals and 250 Hz for the GPS ones. These are the low-level measurements, which are stored in our product in the level 1A subgroup. Just a comparison between GRASS-2 radio occultation instrument on board EPS second generation and the GRASS instrument on board EPS in terms of user requirements. So for what concerns the timeliness, we will have 95% of the occultations which will be made available to the users within 70 minutes, while it was 135 minutes for GRASS. For the regional service, the timeliness is a little bit improved. For what concerns the level 2 atmospheric profiles, we will have these data made available to the users within 150 minutes. Before it was 180 minutes. Number of occultations, okay, for ARO will track GPS, Galileo, and Beidou, so we expect, at least in terms of user requirements, to have 1,700 occultations per day per METOP second generation satellite, while it was 500 occultation per day for GRASS, but it was tracking GPS only. And I have to say that actually GRASS on EPS can track up to 700 occultation per day, averaged every day. We will have the possibility to track 8 parallel occultations, while it was 4 for GRASS. The tracking capabilities allows the radio occultation instrument to track the pilot and data components in closed loop and open loop for the 2 frequencies, L1 and L5, which is a substantial difference with the GRASS instrument that was tracking GPS data on L1 and L2. Open loop in GRASS is performed only on the L1 frequency data. As a vertical coverage, we will go up to 500 kilometer SLTA, while GRASS is going up to 80 kilometer. And as Christian just mentioned before, we are now extending operationally all the GRASS measurement to provide data up to 300 kilometer. But the user requirement was 80 kilometer. Sampling rates, 250 Hertz or 200 Hertz, depending on whether the signal is from GPS or Galileo constellation, open loop and closed loop. Share the same sampling rates, while GRASS is measuring occultation in closed loop at 50 Hertz, and in open loop it is applying a sort of raw sampling at 1 kilohertz. But most important is the bending angle accuracy expected from the instrument and after the processing. So in terms of maximum absolute error for ARO, we expect to have an accuracy of 0.5 microradians in the bending angle measurement, or 0.2% with respect to a ground truth, between 80 kilometer and 35 kilometer. Then the accuracy is decreased a little bit going down to the surface, being expected to be 0.5% at 10 kilometer and 5% at the surface. For GRASS, the requirement on accuracy was 1 microrad. I want really to show these recent results that was presented recently by the industry in charge of developing the radio occultation instrument, which is RUAG Space in Sweden. They developed also the GRASS receiver. So because I want to show this to you, because this is recent results on the end-to-end testing of the first radio occultation flight model. And this demonstrates the bending angle accuracy capability of the receiver. In fact, here the flight model was fed by simulated occultations data, which were generated considering a well-defined atmospheric scenario, and for which scenario the true bending angles associated to each occultation were also known and available. So the level 0 data obtained by the instrument after having been fed by these occultation simulated data were processed by the GPP of RUAG. The GPP is the ground processing prototype, to derive the bending angle associated to each occultation. Then each bending angle profile is compared with the ground truth. And in average, considering 60 occultation, here is the bending angle error profile. So you can see here the blue line is the expected bending angle error. In green is reported the requirement, the user requirement. So we can see that the instrument is performing very well. We expect to have a bending angle well below the limit imposed by the user requirement. And in terms of individual occultations, if here we are plotting the root mean square of the bending angle error between 35 kilometer and 80 kilometer in function of the azimuth of the arrival angle. But okay, it is important to say that this root mean square error is always less than 0.5 microradians. In average, is 0.32, which is the user requirement. So RUAG developed a very, very good instrument, as GRASS was. So some few words about the products that we will generate for the radio occultation missions. So here is our processor. It is fed by a lot of input data for generating the product. In particular, it needs, of course, the level 0 data taken, the level 0 measurements taken by the radio occultation instrument, and the NAVAT data from the satellite. But then it needs a lot of information from the transmitter point of view. So we need to have the GNSS, the transmitter orbits and clock biases, the nav bit message superimposed to the carrier frequencies, the GNSS navigation message, the Earth orientation parameters, differential code biases, and some other service auxiliary files. So all these files are generated and provided by the Ground Radio Occultation Support Network, RSN, that was just put in place, and now the RSN is also used to process the GRASS data as well. But then we need also other kind of auxiliary data, in particular for the precise orbit determination, the solar activity information, the maneuver history file, and the displacement of the center of mass of the satellites in the satellite reference frame, which is stored in this satellite mass report. We need to know also through the instrument database where the antennas are displaced in the satellites within the satellite reference frame. So altogether, they are processed by our processor to generate our product, the level 1B product, which is one netcdf4 file per each occultation. We are going to provide to the users also other kind of auxiliary output files. For example, we are providing the LEO orbit and clock bias file, which are generated every 3 minutes and covers 27 hours of orbits, which is this is the output of the precise orbit determination. We are also providing the original Zenith GNSS data in RINEX files covering 1 hour of observation taken by the POD antenna. I would like also to mention that in order our processor needs to produce the bending angle with a certain accuracy requirement, this famous 0.5 microrad between 35 and 80 kilometers. But in order to do that, we need to take care of also to have a good precise orbit determination of the LEO satellite, as mentioned by Christian before. So the POD accuracy is strongly impacting the bending angle accuracy. And we therefore defined the following set of requirements for the POD. So it is 0.05 millimeter per second for the along track component of the velocity. This is a root mean square value. We need to know the position of the second generation satellite within 5 centimeter 3D position, and the clock bias within 0.5 nanoseconds. Okay, regarding the products, we have one file for each occultation. The file name and the content of each product is fully defined by the EPS second generation generic product format specification. You can recognize in the file name several information, the spacecraft, the instrument, the processing level, and the type bending. Then we have also the information about the product generation time, the start and the end of the sensing of the occultation. And then we have also the information about the satellite, which is transmitting the occulting signal. Inside the product, we have a lot of information. For example, we have the status group, which provides status information on the satellite, on the instrument, and on the processing. But then the most important part is what is included in the data section. This data section contains an occultation group, which is used to store the georeferencing information for the neutral atmospheric occultation, which is georeferenced where the straight line connecting the two satellites is tangent to the VGS84 ellipsoid. Then we have two other subgroups, which are the receiver and transmitter, which are used to store the original orbits and clock of the receiver and the transmitter. For what concerns the orbits, we have the antenna face center orbit and the center of mass of the satellite orbit, both in the satellite reference frame, and this information is stored in the satellite subgroup, and in the inertial J2000, and this information is in the orbit subgroup. We have also Earth orientation parameters. But then in the level 1A subgroup, we have the low-level measurements, which are separated by frequency. These are time series, so we need to provide the measurement epochs, and then we provide also the arrays, the complete arrays of I and Q components and NCO phase. Together, these can be used, are used to generate the total phase, which is also stored in the product. We are storing also the excess phase, so the total phase minus the geometrical part, which okay, is the main observable, or really the time derivative of the excess phase is the main observable for the retrieval of the bending angle, as pointed out by Christian before. We are providing signal to noise ratio time series. We are providing the pseudo ranges. And also we are providing other auxiliary information that might be useful. So we are providing the sampled LEO GNSS orbits, positions, and velocities, the zenith and azimuth of the arrival angle at the radio occultation antenna, the straight line tangent altitudes, and some other flags. For what concerns the level 1B, the neutral bending angle profiles, they are stored in the level 1B subgroup. The bending angle are made available with two different resolutions in the thin and the high resolution groups. The high resolution keeps bending angle on a vertical grid of which is separated by 0.5 meter, while in the thinned group we have a lower resolution predefined vertical grid that is used for a direct data simulation of the bending angle into the at least European numerical weather prediction models. The two subgroups has the same variables inside. We have the Rhinex code of the signals involved in the occultations, but then we have an array of the impact and impact heights, impact parameters and impact heights, the bending angle on L1, L5, the neutral bending angle, the bending angle error, and the georeference information for the tangent points. We have also the ionospheric group, where we are storing all the ionospheric products, basically the profile of bending angles and of scintillations. Tomorrow I will provide some more details on the presentation on applications of radio occultation data in space weather. We have also a quality subgroup. And then all the information, all the details can be found in the EPS second generation radio occultation product format specification. We are providing to the user, to the developer of the ground segment, a sort of test data set. And these test data sets are also made available to all the interested users. These data sets are generated by an instrument data simulator, mimicking the radio occultation instrument. And we are providing 1 day for a summer season and 1 day for the winter season of measurements. In these days, we have basically simulated POD measurements, so GNSS observable for the POD measurements, but we have also 2 orbits for the winter and 1 orbit for the summer scenario, 2 orbits for the summer scenario and 1 orbit for the winter scenario, which contains also simulated radio occultation measurements. So we have more or less 200 occultations here in the summer and 100 occultations in the winter. We are providing level 0 data and level 1B data, which are processed by our in-house prototype. The data set is provided together with the product format specification. And today we have a quite old data set there, but an updated version of the test data will be made available by the end of 2021. For what concerns the level 2 and the level 3 products, these products are generated by the Radio Occultation Meteorology Satellite Application Facility Group, which is led by the Danish Meteorological Institute. They are providing near real-time level 2 atmospheric profiles. I mean, refractivity profile, dry temperature profiles, temperature, specific humidity and pressure profiles. They are providing also the tropopause height and the planetary boundary layer height. Then offline, they are providing also bending angles, level 1B, and reprocessed level 2 profiles, so all these profiles. They are providing level 3 gridded products, which are monthly mean of gridded data for all the variables, gridded in 5 degrees on a latitude bands and on a 200-meter vertical levels. ROMSAF is also in charge to providing in near real time ionospheric product, electron density profiles from 100 kilometer to the orbit altitude, not only to 500 kilometer, and the scintillation indexes profiles. So see the forthcoming presentation from Ian Culverwell for having more details on this. Finally, just one word about the archiving and dissemination. Okay, the data are repatriated after the observations to EUMETSAT, and here we have the payload data processing system that is actually processing the data, is ingesting all the auxiliary files, all the auxiliary data, and is providing for RO the level 1B products to the users through the EUMETCAST and the GTS, Global Telecommunication System standard links. All the details can be found here. Just a final overview on where you can find each product that we are going to generate and which format it is provided to the user. So for the level 1B product at EUMETSAT and for all the ROMSAF products. Okay, that's it. I wish to thank all my colleagues in the radio occultation team. And okay, I'm ready for receiving some questions. Thank you very much.
Hi, Ricardo. Thank you very much for the presentation.
Yeah.
And also for respecting the time you've done it. I will just bring the questions, Ricardo.
Yeah.
Oh, sorry. Present in full screen. So you have stopped your screen. Good.
Yeah.
Yeah. Okay, Ricardo. So I will start with the first question. Slide number 1. Why the RO start from 30 kilometer down to minus 300 kilometer?
This is not true. So in my slides, I was showing that the radio occultation starts from 500 kilometer down to minus 300. So
I think the question, yeah, 500 kilometer down to minus 300 kilometer. That's
so
true.
this is just to have also ionospheric measurements and the possibility to extract ionospheric information also from the occultation.
Mm-hmm. So that's probably what's the purpose of CL pilot data tracking?
Just to have carrier phase and pseudo range measurements in the ionosphere for the monitoring of the ionosphere and for space weather. We have only the pilot data because we need to save the space in the channel that is used to download the data from the satellite. But it is enough because the signal to noise ratio of the antenna induced by the antenna is enough to track the pilot signal and the two frequencies inside the pilot signals up to 500 kilometers.
So the data size, you're trying to reduce the data size or?
No. It's just not to have both the data and the pilot components, which needs more channels, one channel more for the data.
Okay.
RUAC decided to have only the tracking of the pilot component in the ionosphere.
Okay. Mm-hmm.
But it is enough to have ionospheric information.
Okay. Let's take the next
While the
question.
change in L1, L2 to L1, L5, in particular because of the use of the AGA4. AGA4 is this chip, which is the baseband GNSS processor, and it was developed by ESA in particular for tracking Galileo signals. And Galileo has L5 on the civilian signals of Galileo.
Mm-hmm. Good. Is the POD, the precise orbit determination, part of the processing box?
In slide 24, wait. 24. Is the POD determination part of the processing box in the middle? No, the processing box, okay, if I can quickly share.
Yeah, I stopped
my screen. No, I can do this. So you can see
please.
here, this is the entire processor. So the processor is the level 1B processing plus, and before the level 1B processing, we have the precise orbit determination component. So is everything included here.
Okay.
Okay.
Mm-hmm.
Wait.
Okay, yeah. I bring up again. Yeah, it's okay. We have relaxed, pretty much relaxed. Next question, Ricardo. In your synthetic modeling of residual error, reference to slide 22, what kind of ionospheric EDP model did you use, and did it have asymmetry around the tangent point? How do you expect? I can't how do you expect asymmetry around ROEDP nominal point
Oh,
effect error? Thank you
okay.
from Robert.
Okay, so in your synthetic modeling of residual error, but here, so here I can share again the screen. What
Slide 22, I think.
is this? No, so this is slide
Yeah.
22.
Mhm.
So this is let me say the results of an end-to-end testing performed on the flight model. So they RUAG simulated occultation signal based on a certain scenario where we have the neutral part of the atmosphere, okay, defined by the CMLWF data. And on the top of these, we have also the refractivities from the ionosphere generated with realistic ionospheres. But for the ionosphere, so that then the way that this signal is simulated, the occultation signal is simulated, is to going through a wave optic propagator which assumes spherical symmetry. So then we this wave optic propagator generates the signal that is expected to have in the LEO orbit up to 500 kilometers. But then here the results are shown only below 80 kilometers in terms of bending angle. Also because, let me say, the bending angle requirement is only, I can show you this slide, the bending angle requirement is only defined up to 80 kilometers. So we don't have any requirements on the bending angle accuracy above 80 kilometers. So any things that you can think about how the ionosphere plays a role here is not taken into account in showing this kind of results.
Okay.
I don't know if I answer to the
I think
to the question.
I think that was fine. Yeah, I then bring back my slide. I think there's one more. I think that we answered how do you expect a symmetry around. Yeah, okay. I think you've answered it. Yeah.
Can we extract ionospheric information from our observations? Was impact height is equivalent to atmospheric height, less than 80 kilometers? But we will start, or people who is doing data simulation into space weather or ionospheric models will start to ingest data from radio occultation instruments, which are basically, okay, we are going to provide electron density profiles starting from 100 kilometers. But normally these data simulation models can ingest also data slant tech, so this slant total electron content that can be measured by in the radio occultation link. So these models can start to assimilate also those data which are below 80 kilometers. But I think that the ionospheric models will not start well below 80 kilometers. At the end of the story, the ionospheric models will model the ionosphere. The output will start above 80 kilometers, as also pointed out by Christian before.
Okay.
And then, is there a way you think to combine GNSS ground and radio occultation observation? Yes, for sure. In these data simulation models or in the tomography, you will, for sure, people that is doing this is for sure combining ground GNSS observations with LEO GNSS information. And then thinking about the way that the limb sounding is working, in the tomographic approach, you have the limb sounding is providing the vertical variation of the ionosphere, while from ground you have more information about the vertical, well, the horizontal variation of the ionosphere. So we have two complementary informations from the ground and from the ionosphere, from the space, that can be for sure used for tomography and for data simulation.
Okay, that was your last question, Ricardo. I stop share before we go for the break. I also have a short announcement. We've been constantly trying to improve the webinar experiences. We may have more coming up. So you can indicate your feedback to us in a poll in Slido again. So you have a link there in the chat now, how to do this. So, this is for today's session, how you found the talks, and if you have any feedback on how we deal with these webinars today. please express them freely there. You are anonymous. It's just for us to improve ourselves. Thank you very much. So with that, Ricardo, thank you very much for the presentation and for answering all the questions. Very interesting session. So I think we go for a break and we come back at 1:30, 3 CEST. I think it's 1:30 UTC. Okay. Thank you.
Thank you very much.
Until we meet again, stay tuned. Hi, Yen.
Hi, Sarika.
Hey, you can bring up your slides, actually.
Okay, let's whoops, entire screen. Very good. Like that?
No, you don't see anything.
Okay.
I think try the way you tried before, you know, sharing the...
Yeah, that is what I've just done. Yeah, sharing the entire screen. Window or screen, entire screen. Let's allow. Yeah.
I see myself.
Yeah.
I think it
might...
might...
Do you see this now?
Yes, but put it in full screen mode. Yeah.
You got it now?
Yes.
Yeah.
And you can start, the first slide is up there, so you can start straight away, and good luck.
Okay, thank you. If it's the time, is it? All right. Well, all right. Hello, everyone. My name's Ian Culverwell. I work at the Met Office in the UK on the radio occultation processing package, and I'm giving this talk about that on behalf of the ROMSAF project team. So, what is ROPP? It's a comprehensive software package. The initial and still primary intention is to help users prepare RO data for simulation in NWP systems. And it is a collection of software modules in Fortran 95, build scripts, data files, documentation. And it's a deliverable of the Radio Occultation Meteorology SAF, which is a decentralized processing center under EUMETSAT. It's quite a mature product now. The first release was 14 years ago, version 1.0. The latest release, version 10, was February this year, and there will be another one, version 11, in January, February next year, assuming it's approved for release. And currently, ROPP releases are managed by the Met Office in the UK, which is why I'm giving the talk. It has a modular structure, collection of modules which are in principle independent, although in practice most people tend to just use them, just tend to download an entire new release and update all those modules at the same time. And there are various dependencies shown by these arrows here, that the tail of an arrow, head of an arrow depends on the tail of the module at the tail of that arrow. So I'm briefly going to go through each one of these 6 modules just to show you the what's in ROPP. The first one is...
Yen, can I interrupt you for a minute? Your voice is kind of going up and down. It's not uniform. It's sometimes fading, but sometimes too loud. So I don't know what the issue could be, but
I don't know what I can do about that. I've got a headset on.
When it is loud, it's a bit too loud. Maybe you're moving and going away from the microphone sometimes, and could be that.
I've got the headset on.
Okay.
I've got my headset on. I'm not moving at all.
Okay. Try doing again, and if there is a problem, I will tell you. Yeah.
Well.
Okay. Put this presentation in the full screen as well. Yeah.
Yes, I'm just going to do that. Right. So the ROPP utils module that consists of a set of low-level service utilities, quality control, range checking tools, conversion routines between various coordinate frames, inertial and earth-centered frames. Of reference, the geopotential geometric height conversion routines, date-time conversions, and unit conversions, and that's used by all the other modules. Depending. Here's a little example of something courtesy of Hans Gleisner at DMI, something that went in to ROPP a few years ago, converting inertial frames used by EUMETSAT here at the top, and the true of date inertial frame used by UCAR, and obviously it's important to get those two to talk to each other so that we can compare the two. So that's just an example of the sort of thing that's in the utilities module. The I/O module is also used by all the other modules. ROPP has its own internal NetCDF based data structure, which is fully described in the documentation, and we can read data from that same structure and do things with it. We can read data from buffer format, from UCAR format, the atom fizz and the atom proof files that some of you may be familiar with. GFZ manage the GRACE and Tandem X satellites. They have their own proprietary format, set of pair of ASCII files which we can read in. Grid, we can give us a grid file, and we can extract a profile for use in as a background, for example. And what I've just loosely described there is EUMETSAT formats, which is something like the things that Ricardo was just describing a moment ago, the processor production facility, profile production facility. We can read all those formats, and we can write out in ROPP and buffer formats. And there are the sort of administrative features like profile thinning, inverting, extracting, and merging profiles. So here we are. This is basically the same thing, but just in schematic format. Buffer, we can. There are 3 different buffer libraries that we support currently. The 2 UCAR types of file, GFZ files, the grid files, edition 1 and 2, and these PPF files from EUMETSAT. We can read all of those in and produce standard ROPP format file. And we can also, in one case, go backwards and produce buffer files from that ROPP format. The PEP module, the pre-processing module, that does this calculation from excess phase, which Christian was mentioning at the beginning of today, to bending angle, refractivity, dry temperature, and so on. Christian also mentioned, saved me the job, about the types of processing that you can do. That geometric optics, so you treat a set of rays, effectively taking the wavelength to 0, but also in the presence of strong vertical gradients near the surface, then you will need wave optics processing. And ROPP has the ability to do both of those. It can do ionospheric correction, which is the combination of the 2 signals to get you some feel for the neutral atmosphere bending angle, and statistical optimization, which is a clever way of doing the same thing, basically. And also, again, quite recently, wave optics propagators have been introduced into ROPP, which are in a way the reverse of the usual pre-processing routines. Here you give a model refractivity field, either spherically symmetric or a 2-dimensional one, a slice of refractivity, and you calculate in idealized situations what the accumulated excess phase would be at your receiver. And that's useful for processing and sensitivity studies and things like that. Just a quick example of just one processing example. On the left leftmost picture, we've got the signal to noise ratio of a rising occultation. You can see here, because the signal to noise is increasing, it's getting clearer as the ray rises through the atmosphere. And we've got L1 and L2 marked separately there. The next slide along, the second one along, is the excess phase, which Chris was talking about, and you can see it drops off very quickly, no log scale, as we go up into the, as we rise free of the Earth's atmosphere. From that, the BP module can produce bending angles in the third picture, the L1 and the L2 ones shown there. And the last picture shows what happens when you do the ionosphere correction, just the linear combination, LC it's shown there, of the two frequency-dependent bending angles, and try to subtract out the ionospheric components. And you can see you get a much clearer estimate of the, or a much cleaner fall away of the bending angle. So the log scale, so it's dropping away exponentially with height. Opt here is the statistical optimization version, which you can see is doing a better job up here, because you're starting to take the difference of two numbers which are rather close to each other and with rather big errors. So it's it just doing the straight difference gets a bit noisy, as you can see. Anyway, that's the sort of thing that the pre-processing module can do. The FM model is the forward model. Give you a background feel of temperature, humidity, pressure, and it can calculate the refractivity and the bending angles. That's the forward operator. It also calculates the gradients, the Jacobian matrix, if you like, of those, and the tangent linear and the adjoint models as well, which will be used in the 1D bar module, which I'll come up to in a second. And we can cope with models on or it can cope with models on hybrid signal levels like ECMWF or geopotential levels like METOFICE. And we can generate bending angles from 1D, that's to say a spherically symmetric field, state vector, or a 2D, a slice, two-dimensional background field. Here's just a little example of this. Leftmost picture is the pressure as a function of height, and the middle one gives you temperature and specific humidity, again as a function of height. And on the rightmost picture, you've got bending angle in red and refractivity in black that are produced by those input files, those input fields. The 1D VAR module that takes a background state from a model, almost always, and observed bending angles or refractivities, and uses that to construct a 1D VAR retrieval, a best estimate of the state vector, the temperature, the pressure, humidity, that is consistent with those two, a priori background model and the observations which it doesn't match. So I've said we can do refractivity or bending angle. We can also use ECMWF or METOFICE background profiles. Quality control is taken out to prune out obviously dodgy data. The error covariance model, if you know about 1D VAR, you'll know that the results are crucially dependent on the model and the observational error covariance models that you use, the matrices, and a variety of those are supported in ROPP. And usefully, there's some diagnostic output. It tells you things like the cost function at the end of the process, the 2J over M's, things like that, the O minus B's, the O minus A's. So you can see whether it seems to be working. Here's just one particular example. The leftmost picture is a bending angle in green. I hope you can see. So if you can't, falling away exponentially with height. And in blue here, we've got the O minus B sort of normalized. So the yes, background field, the forward model background field, taken away from the observed bending angles. And in red, we've got the same thing for the solution, the forward model solution. And you can see it's a little bit smaller, which is what you would expect. The central picture is the temperature difference that results from doing that, and we can see so the temperature itself is in blue, and the solution minus the background, the analysis minus the background is in red, and we're getting maybe a couple of degrees difference in temperature on this one profile. And likewise for humidity, background in blue, and we're seeing perhaps 1 gram per kilogram increment to the specific humidity. There's an applications module, which does bits and pieces that don't fit in anywhere else. Currently, that just has 2 things in it, something to diagnose tropopause heights and something to diagnose planetary boundary layer heights. You'll remember from Ricardo's presentation that these are going to be produced by EUMETSAT, and yeah, and this is the tool that it's going to use. Here's one example, tropopause height, and the leftmost picture is the bending angle. Again, in blue here, you might just be able to see a little kink in the profile about there. We pass this through a covariance transformation, which is basically a wavelet transform. You know what that is, and it accentuates this kink. You can see here, and the maximum of that, the peak of that, is taken to be the measure of the tropopause height. We do the same thing with refractivity, again in blue here, a little kink about there. Covariance transformation picks out this point of the tropopause height. You can do this for the dry temperature, which is a sort of processed version of the refractivity. And there are 2 measures of tropopause height you can make from temperature. One is based on the lapse rate, to the WMO definition, when it falls below a certain value, and one is based on the cold point, which is when the lapse rate is 0, when you've reached the minimum temperature. And both of those are produced in ROPP, and you can examine and do that. We also provide the facility to do the same thing with a background profile. Quite often you have background profiles, co-located background profiles, and you may come from a model, and you would probably, or you might be interested in seeing how those compare with the observational tropopause heights. And this is what we can do here. We can do a similar thing with the boundary layer heights around a picture. So, ROPP development, that's a quick overview of the sort of things that ROPP can do. The development is overseen by the steering group. Large developments are covered by work packages, which are agreed by EUMETSAT at the beginning of each 5-year development phase of the ROMSAF. Medium-sized developments, we have these coordination group meetings, trying to decide which ones are most important, and if it needs, if there's dispute, if it can't be resolved, then the steering group will choose what to do, and small developments we just do as part of the general release management. Currently, development is carried out in quite a creaky track-based system. That's going to be moving to a GitHub session, GitHub system within the next few years. And there is a help desk for user inquiries and requests, so general users can say, I think this would be good, think about it, and that will get fed through and included in for consideration anyway. Release management, you're probably not too interested in this, but do probably what you would expect. Branches emerged into a prototype release. This undergoes beta review by experts outside the ROMSAF, and then we run it through a test folder, which does lots of tests on lots of different compilers and different platforms, and we need to make sure that it's robust to those sensitivities. Supporting documentation is written and distributed to users, of course. Release notes, change log, user guides. The suitability of the code is assessed in a delivery readiness review, and then the steering group approve it or don't approve it for release. It's just an example of a test folder, so you can see, perhaps you can't read these, none of these are different compilers on different platforms, and these are different sort of tests of the IO module, the FM module, 1D bar, and so on. And sometimes we expect failures. In this particular case, this is a regression test where we compared the results of the run against the immediately preceding release, and we made a change which we would expect to cause a failure, and which it did. If we hadn't seen a failure there, something would have been done badly wrong. Finally, accessing ROPP, go to the ROMSAF homepage. Down in this column here on the left, there's software. Click on that. You get to this page. There's another piece of software, GBGP, which I haven't spoken about, ground-based processing system. But go to that and you'll find ROPP as your default position. You'll need to sign a license, but once you've done that, go to the download page here or here, and this will take you to the ROPP package download. You can see there's a README file, licenses, copyright notice, release notes, the change logs I was just talking about, and the complete package distribution. It's a single tarball which you can download, and using the information in the release notes, you can build it for yourself. But finally, then, the summary is really a repeat of what I just said, what I said at the beginning. ROPP is a collection of software tools, mainly to help people simulate IO in NWP systems. Software modules owned by the ROMSAF, actually it's owned by EUMETSAT, but it's deliverable by the ROMSAF. And next release early next year, and currently managed by NetOffice. So that's all I have to say. Thank you.
Thanks, Ian. Sorry to say there were it was not very smooth hearing. Sorry about that, but I think you couldn't do much about that either. So it's okay.
I don't think I can.
Yeah.
Wearing headsets and yeah.
So can you stop sharing your screen maybe, because I see myself and I think a lot of others are seeing me. No
Has
problem.
It stopped?
Yes, it has stopped, Ian. Yeah.
Stopped. Okay, good.
No, it's fine now, Ian, and perhaps there's some problem with the connection, or anyway, that was a good talk, interesting talk. I will bring up some questions, Ian, for you.
Yeah, sure.
Yes. Oh, no, sorry, that's the... Oh, okay. I think this was a question for, I can maybe bring up the recent questions. Okay, let's do that then. Is ROPP used only by the NWP community? So the applications of ROPP.
Depends how broadly you mean NWP. It's certainly used by researchers who are interested in things like tropopause height, boundary layer height, these sorts of things. Is that NWP community? It's not used just by operational centers, if that's what the question meant.
Okay.
But yeah. Can ROPP read nets? Sorry, go on.
Can ROPP read NetCDF format?
Well, depends what NetCDF format. It can read files that are in the ROPP NetCDF format. It can read files that are in the UCAR formats, the AtomFizz and AtomProof formats. But yeah, it's not a NetCDF reader. So yeah. It doesn't just open an interface and you can pick and choose what you want.
Maybe the question is, you had several formats there with EUMETSAT, PPF format, but maybe for EPS-SG, we'll have the RO data in NetCDF format. Maybe that's where the question comes from. So if it can read
and we can do that. Yeah, that's right. That will be.
I think that's probably because we had Ricardo's talk before suggesting this. Okay, could be that. Yeah. Mm-hmm.
I think that's, and we can read those as well. Yes.
Mm-hmm. Okay, thank you. Is ROPP supporting ionospheric retrievals? I think so. Yeah.
Not yet, but it might do in the next release. That's the big thing that we're introducing in ROPP 11 in the new year. We'll be able to. We've been working on a way of getting that from the difference in the bending angles, and yeah. So not yet, but soon.
Mm-hmm. Great, thank you. What does a thinning algorithm do?
It just means reducing the size of for example, a set of bending angles. You can reduce the number of them, and there are various thinners available in ROPP, but we don't use it very often because we tend to use the same set of bending angle levels. But it just, yes, it just means reducing the volume of data without, you hope, throwing away useful data.
I think this was asked before. What's an ROPP format?
Well, it's a particular type of NetCDF format, and it's described in the documentation. It can hold level 1A, level 1B, level 2A, 2B, 2C. Yeah, I don't know what it's described in the documentation. It's our own kind of internal.
Okay. What would be the expected latency of RO data release versus the occultation real time? It's probably not a question only for you, but maybe Ricardo or Christian, would you like?
I don't know that. Go ahead.
Ricardo or Christian, can you?
Yes, I guess I shown a slide on this because the near real-time data level 2 products that will be released by ROMSAF for radio occultation will be provided within 100 and I guess 150 minutes from the observation.
Okay.
Yeah. But it's in my slide.
Yeah, Ricardo, while you are there, maybe this is also for you. What does minus
300 kilometers is the straight line tangent altitude, is the distance between the straight line connecting the two satellites during the occultation from the Earth's surface.
Okay.
Because of bending, it is going down the Earth's surface, of course, is the distance from the Earth's surface.
Okay. Thanks, Ricardo. Thanks also, Ian. Thanks for the great talk. I think with that, I think we finished all 3 talks from today, and we look forward for tomorrow's sessions where we are talking about more the applications of RO in 3 different areas: in numerical weather prediction, in climate, and in space weather. And I thank all of today's speakers and also all of today's participants who attended this, and also my support, Regina and Stefan. Please, again, go to the polls and express your opinions. We are eager to hear that. And with that, I end today's session. Once again, thanks to all speakers, to Christian, Ricardo, and Ian. Thank you very much.
Thank you to you.
Bye-bye.
Thank you.
Bye.
Bye.
Bye-bye.